Welcome! Today we are exploring the foundational concepts of electricity, a force integral to virtually every instrument and device we use daily. Our focus is on understanding electricity from its atomic roots to its practical applications in circuits and power distribution. Clara, this module provides an overview of electrical circuits, touching on atomic theory, basic electrical theory, and even how we measure electrical quantities. Could you start by giving us a broad picture of what we're aiming to understand today?
Certainly. We're going to demystify electricity, explaining that it's all about cause and effect. The text points out that to grasp electrical theory, we first need to understand atomic theory. This module introduces fundamental concepts like atomic structure, the distinction between conductors and insulators, the role of magnetism, and the basics of power distribution systems. We'll also cover essential electrical units of measurement, how to use Ohm's law and the power equation to calculate unknown values, and even how to read schematic diagrams. We'll also define current, voltage, and resistance.
That's a lot to cover. Let's start with the very beginning, the atom. The module states that electricity fundamentally comes down to atomic theory and the transfer of electrons. What are the key components of an atom that are relevant to understanding electricity? So electricity boils down to these tiny charged particles. The module mentions positive and negative ions and how charged particles either attract or repel each other. Can you elaborate on the law of electrical charges?
Absolutely. The law of electrical charges is quite straightforward. Particles with like charges repel each other, meaning a proton repels another proton and an electron repels another electron. Conversely, particles with unlike charges attract each other, so a proton attracts an electron. This push and pull, governed by electrostatic force, is fundamental to how electricity behaves. The source also notes that the negative charge of an electron is equal to the positive charge of a proton, and these are called electrostatic charges.
That makes sense. Now, how do these atomic structures explain why some materials are good at conducting electricity and others are not? The text distinguishes between conductors and insulators based on their atomic structure. The key lies in what we call the valence shell, which is the outermost ring of electrons orbiting an atom. The electrons in this shell are called valence electrons. An atom's ability to gain or lose these electrons determines its electrical properties. Conductors typically have 3 or fewer valence electrons, which are easily dislodged and can move freely, allowing current to flow easily. Materials like copper and silver are excellent conductors. These valence electrons are the ones of most concern because they're the easiest to break loose. And insulators? Insulators are the opposite. They have 5 or more valence electrons, which are tightly bound to the atom and not easily freed. This makes it difficult for an electric current to pass through them. Porcelain and plastic are common insulators used to prevent electricity from flowing where it shouldn't. There's also a third category, semiconductors, which fall in between, having 4 valence electrons. For example, germanium and silicon are semiconductors. So the number of electrons in the outermost shell dictates whether a material will readily allow current to pass or not. Beyond just the flow of electrons, the module also discusses magnetism. How does magnetism relate to electrical devices?
Magnetism is critical to many electrical components. Devices such as motors, relays, transformers, and solenoids all rely on it. The text explains that magnetized iron generates a magnetic field. Interestingly, electricity also produces magnetism. When current flows through a conductor, it creates a small magnetic field around it. If you coil that conductor around an iron bar, you create an electromagnet. This electromagnet then acts just like a regular magnet, attracting and repelling other magnetic objects. This principle is fundamental to how electric motors operate.
That's a powerful connection between two seemingly separate forces. Moving to a more practical application, how is electricity distributed to our homes and businesses? The module mentions a large power distribution system.
Electricity originates from generating plants, whether they're powered by coal, nuclear energy, hydro, solar, or wind.
These plants use turbines to generate electricity. This power then travels through long-distance transmission lines, sometimes at voltages as high as 750,000 volts. To make it usable and safe, devices called transformers are used to step the voltage down as it moves from substations to neighborhoods and finally to homes, offices, and factories. For example, homes typically receive 240 volts, with standard wall outlets providing about 120 volts for small appliances. Commercial buildings can receive anywhere from 208 V to 575 V.
It sounds like a complex but well-orchestrated journey from power plant to outlet. The module also includes a section titled, "Why Bother Learning Theory?" It poses a question, why learn how something works if you only need to install it? What's the module's answer to that?
The text emphasizes that just knowing how to install something limits your capabilities. If you only know the how, but not the why, you become a parts changer. If a system fails, you would have to replace components one by one until you stumbled upon the solution. Understanding the underlying theory, like atomic structure and electrical principles, allows you to troubleshoot effectively. It means you can diagnose and fix problems, not just swap parts, which ultimately means there's no limit to what you can accomplish.
That's a compelling argument for understanding the fundamentals. So this initial module lays the groundwork for understanding current, voltage, resistance, and power, and how they relate through principles like Ohm's law and the power equation, even teaching us to read schematic diagrams. It seems like a comprehensive start to electrical knowledge.
Precisely. It sets the stage for a deeper dive into practical electrical work by ensuring a solid theoretical foundation. We covered the basics of defining current, voltage, resistance, and calculating power.
If you found this conversation insightful, consider sharing the episode with someone interested in understanding the basics of electricity.